A-Level Chemistry Paper 2, Specimen Set 2. So question 1 first of all gives the initial rate, and it gives the concentration of benzaldehyde, which is this chemical here, and it gives the concentration of benzaldehyde in each of these 5 experiments, and it asks you to calculate the concentration of benzaldehyde squared. So all we do is take 0, square it, 0.25 square it, 0.5 square it, 0.75 square it, and 1 square it, and you come out with answers like that. There are no marks for precision, so you can run it to as many decimal places as you want, really. Plot the graph of this benzaldehyde concentration squared on the grid opposite and label the axis. So it'll come out a little bit like this, where you've got initial rate up the side and benzaldehyde concentration along the bottom. You always do it that way, so something that's fixed in the table goes along the x-axis, so the concentrations here are measured, are sort of laid out at the beginning of the experiment, and these are the results that you take. So the results that you take, like the rate, that aren't fixed concentrations, this is what you're measuring, goes up the side. Deduce the order of reaction with respect to benzaldehyde from the graph. Explain your answer. Well, normally a straight line is first order reaction. So if something's first order reaction, then usually it means that 0 order is a straight horizontal line, first order means it's a straight line going up like this, and second order would be a curve curving up like this. But because you've got squared on the bottom, actually a straight line in this case is showing second order. So normally if it was just concentration of benzaldehyde, a second order reaction would curve up like this. But because you've got a squared here, the squared actually turns it into a straight line. So if the concentration is squared along the bottom and it's a straight line, it's actually second order. So it's second order, and that's because concentration squared plotted against the rate is actually a straight line. If it weren't squared, then it would be a curve bending upwards. Let's have a look at this next one now. The rate equation for the reaction is rate constant multiplied by the concentration of benzaldehyde multiplied by the concentration of some cyanide ions. But actually cyanide ions don't appear in the actual reaction, but they do affect the rate. So that's strange, isn't it? They're not a reactant, but they affect the rate. So explain the role of something that affects the rate, can maybe speed up a reaction, but it actually doesn't appear in the equation at all. Maybe it's there at the beginning and there at the end. Maybe it's remade and therefore it can cancel both sides, but it doesn't appear as a reactant or a product in the rate, in the sort of reaction at all, but it does affect the rate. So the role of a Cn- ion is it's a catalyst, and because it appears doesn't appear in the equation but does appear in the rate equation, that means that it's a catalyst. So this question is about halogenoalkanes in the upper atmosphere, chlorofluorocarbons and ozone. When you have a chemical like chlorine, or a chemical that's got chlorine in it, like a chlorofluorocarbon that's got a C to Cl, so it's got a chlorine atom in there, that covalent bond can break. It can break in the upper atmosphere in the presence of UV light. And the UV light provides some energy, and the pair of electrons in the C to Cl covalent bond, one electron goes back onto the C, and one electron goes back onto the Cl. So in other words, the share that they've set up is broken and they get their electron back. That creates a chlorine atom again. Instead of it being in a covalent bond with the Cl, it's reformed as an atom. Now the only difference is that we show the unbonded electron, the electron that was once in that bond, as a dot. It's an atom, so chlorine atom is sometimes called a radical. It's an atom that's reformed, it's an atom that was once in a covalent bond, and to show that it's got its electron back, we show that as a dot. It's called an unbonded electron, and it forms when that C to Cl bond breaks, or in some cases if you've got chlorine itself, ClCl or Cl2, it's when Cl2 breaks or when CCl breaks. So a bond between a Cl and a C, or between a Cl and another Cl, when it breaks in the presence of UV light, the two atoms break the covalent bond and the atoms get their electron back, and you draw it as a Cl dot, which is a chlorine radical. That is its unbonded electron, the electron that was once in that covalent bond. But to all intents and purposes, it's a chlorine atom. If something's a Cl dot, then it's very reactive. And what actually happens is the Cl dot reacts with ozone. Now ozone is O3, you need to remember that, O3 for ozone, and it makes something. You can't remember this, but you can remember this, O2. O3 always makes O2. There's only two forms of oxygen, O3, ozone, and our sort of normal day-to-day oxygen that's in the atmosphere that we use for respiration is O2. Now you can work out what's left. So I've not used a Cl. There's 3 O's there, 2 O's there, so there must be an O and a dot. So you can always work this out even if you can't remember it. Now, which of these are going to react again? ClO dot is a radical with an unbonded electron, so that's going to react again. It reacts with more O3, so this ClO dot, this radical, reacts with more O3, and the only thing that it can make is O2. Now you can balance out the O's. I've got 4 on the left. I can balance it out by putting a 2 in front of the O2, and that means all the O's are now balanced. The only thing that I've got is a Cl and a dot. I've remade the chlorine radical. It's a catalyst. This is called a chain reaction where it goes on and on and on. The Cl dot is remade. It's a catalyst. That's why one Cl dot from a chlorofluorocarbon or from chlorine in the upper atmosphere in the presence of UV light, one chlorine radical can react with an awful lot of O3 and can cause holes in the ozone layer and some skin cancers. Chloroethane reacts with potassium hydroxide in the presence of propan-1-ol to form ethene. So potassium hydroxide can do two things. It can either, in the presence of cold water, it can do something called nucleophilic substitution, and it can replace the Cl with an OH and make ethanol. But in this case, if it's making ethene, usually because it's in warm ethanol or warm ethanolic solution, it's called an elimination reaction. And the mechanism is actually this. It's a 3-arrow mechanism where the OH- uses its lone pair to attack an H next on the C next to the C of the Cl. So if you find the Cl and trace it back, the Cl is joined to that C, which is joined to a neighbouring C, and it's one of these H's on the neighbouring C of the CCl that gets attacked. When that H reacts with an OH-, it makes water, because this OH- is giving electrons away to bond to the H. So now I've got H2O, and it's given electrons away, so it's lost its minus charge. The electrons from the H now, so this H is bonded with the OH, the electrons in that C to H bond move in between the two C's and form a double bond, and the Cl is broken off. The Cl is electronegative anyway. This is a polar bond with a slight delta minus charge on the Cl. It's electronegative, drawing electrons towards itself, and it breaks and goes onto the Cl. And because electrons are moved onto the Cl, that becomes Cl minus. So that's the mechanism that we're looking at, and it's elimination because this chloroethane has lost a Cl and it's lost an H, so it's had atoms eliminated from it. The role of the potassium hydroxide. So the role of potassium hydroxide, it's not a nucleophile. A nucleophile would attack that C there, that C with a delta plus, and eliminate the Cl, and it would form ethanol. So it's not a nucleophile. It's actually, if you have a look at it, OH- becomes H2O. So it's gaining an H and it's losing the minus. It's actually gaining an H+. Something that accepts an H+ is called a base. What's the role of the propan-1-ol? Well, the propan-1-ol doesn't appear here at all. So what's the role of the propan-1-ol? You might think it's a catalyst. It's a tricky question. It's actually not a catalyst. What it's actually doing is it's allowing these two chemicals to react together, because this chloroethane is not really soluble in water, and this is soluble in water, but they're both soluble in propan-1-ol. So it's a solvent. It's used to dissolve both chemicals to allow them to react together. A tricky question, that. It's allowing both of these chemicals to mix. Name and outline a mechanism for the reaction. Well, we've done that already. We've decided it's elimination and we've talked this one through. The structure of polymer A is shown below. Draw a structure of the monomer used to form polymer A. Well, I've got a backbone of carbon atoms here. So the backbone of carbon atoms means it's been addition. It's an addition polymer. It's formed from addition of unsaturated monomers, so short chain molecules with a double bond. And you've got to find the repeating unit. So if you find the repeating unit, the repeating monomer is this, CCFFFCl, and you can see that repeats itself 3 times here. So I find the short repeating unit, and the way that that's joined together is once upon a time it's had a double bond in between the two Cl's that has broken and formed a long chain. A difficult question this, and in 2 parts, so question 2.5. First of all, the first section is not too difficult. Chemical analysis shows that chlorofluoroalkane B contains by mass 51.5% fluorine, 32.1% chlorine and no hydrogen. So the remaining part is carbon. So first of all, if you work out 51.5% fluorine, 32.1% chlorine, the remainder must be carbon. So by subtraction from 100%, 16.4% is carbon. You divide the atomic mass of each of them into those percentages. So 51.5 divided by 19, that's the atomic mass of an F atom, a fluorine atom. 32.1 divided by 35.5 is the atomic mass of a chlorine atom, and 16.4 divided by 12, the mass of a carbon atom, gives this ratio. And then you divide by the smallest. So the smallest is 0.9, so if you divide them all by 0.9, it gives a ratio of 3 to 1 to 1.5. Then you multiply up into the largest whole number, so if I multiply them all by 2, that equals 6 to 2 to 3. So in there there's 6 F's, 2 Cl's and 3 C's, so the molecule is C3F6Cl2. The molecular ion that we're trying to find, so a molecular ion is the whole molecule minus an electron. So what's actually happened is that electron impact ionization, so in a mass spectrometer, means that an electron gun has been fired at this and it removes an electron and forms a plus ion. So all you've got to do is take the molecular formula and add a plus onto it. The next section is more difficult. So the next section now is, it says, determine the formula of each of the 3 molecular ions of B. So I've got 220, 222 and 224. So what are my 3 combinations? Well, my 3 combinations are including 35Cl and 37Cl. So I could have a 35 and a 35. So remember, I've got 2 Cl's in here. So I've got 2 Cl's. So I could have a 35 and a 35. I could have a 35 and a 37, or I could have 2 37s. So they've either got to be both 35s, one of each, or 2 37s. If you add up the MR with 2 35s, 2 35Cls, that's going to give the lowest MR at 220. A 35 and a 37 will give a slightly higher MR at 222, and a 2 37s will give a 224. So that then gives you this here. So this here, so 2 35s, 220, 35 and the 37, 222, and a 37, 2 37s gives a 224. Okay, so those are the combinations. Now, predict and explain the ratio. So the final couple of marks are the ratio, and this is more like a probability question than anything else. So if you actually consider that if you look at the combinations of these, so somewhere or another it will tell you it has the 2 isotopes, 35Cl, 37Cl, in the ratio 3 to 1. So out of 4 atoms, 3 of them are 35 and 1 of them are 37. So 3/4 of them, 3 out of 4, if I had 4 atoms, 3 would be this and 1 would be 37. 3/4 would be 35Cl and 1/4 would be 37Cl. So what you actually do is, if I've got 2 35s, the chance of getting 1 35 is 3/4, the chance of getting a second 35 is another 3/4, and what you then do is, to work out the chance of getting one of the Cl's is 3/4, another 35Cl is another 3/4, you multiply the two together. 3/4 times 3/4, well, you could do it on a calculator, equals 9/16. you multiply the two fractions together. That's what you do. It's similar to, say for example, the chance of throwing heads are 50% multiplied by 50% is 25%. So it's a probability question. What's the chance of getting two 37s then? Well, there's a 1/4 chance of getting one 37, another 1/4 chance of getting a second 37. 1/4 times 1/4 is 1/16, and the remainder then is that. So you could work out the remainder, 10/16, the remainder is 6/16. So you could just do that by subtraction. Or you could say, if you wanted to work it actually out, then the chances are 3/4 of this one is a 3/4 chance of 35 Cl, a 1/4 chance of 37 Cl, that's 3/16, and one of them is at carbon number 1, one's at carbon number 2, or they could be the other way around, 3/16 and another 3/16 are 6/16. Although, as I say, if you work out that the first one has got a chance of 9/16 and the second one has got a chance of 1/16, that's 10/16, so the remaining part is 6/16 for this one here, MR222. Question number 3. How many isomers are represented by C5H12? So there could be 5 in a line, which is pentane. There could be 4 in a line with a methyl group at number 2, 2-methylbutane. 2-methylbutane and 3-methylbutane are the same thing. It just depends which end you start labeling from. Methylbutane or 2-methylbutane, same thing. Or I could have 3 in a line propane with 2 methyl groups on number 2. So I could have dimethylpropane. So there are 3 different isomers. Name the type of structural isomerism shown by C5H12. So structural isomerism, remember, is the same molecular formula but just a different structural formula, so it's drawn in a different way, in a different structure. And there are 3 types: chain isomerism, where the length of the chain changes; position, where the position of a functional group changes, maybe a double bond changes its position, or an OH changes its position on the chain; and a functional group, where the actual functional group changes, so maybe it changes from a double bond to a cyclic set of single bonds, something like that. In this case, pentane has shortened its chain to methylbutane, shortened its chain again to dimethylpropane. It's chain isomerism. So the next one, 2-hydroxypropane nitrile, displays optical isomerism. So I've drawn you 2-hydroxypropane nitrile here. Let's just have a look at it. Prop, 3 in a line. 2-hydroxy, so an OH is either an ol or an hydroxy. Propane, 3 in a line. Nitrile is a CN, and the C, one of the C's counts as part of the chain. So I've got 3 carbons in the chain. This is a nitrile, and since this ends in the word nitrile, and by the way, that C is always number 1 there, the C of the CN is always at number 1 because this group is always at the end of a chain. This makes this number 2. And since I've used the ending nitrile, I need to name this as a group, a hydroxy group. Now it says draw 2 3-dimensional representations of the 2 enantiomers. So this is an enantiomer because the carbon in the middle is a chiral carbon or an asymmetric carbon. It's got 4 different groups attached to it, so it's going to have mirror images enantiomers that will rotate plane polarized light in different directions. So let's have a look at this. So I've got to draw the 3-dimensional representations of this. Normally you can get away with just drawing a 2-dimensional representation, drawing a cross shape and then drawing again with the CN on this side and the CH3 on the right hand side, the OH up and the H down. But it wants you to do a 3-dimensional representation. So what you need to do is you need to draw the OH and the H, or any of these groups really, let's say the OH and the H, and then one coming forward, let's say the CN and the CH3 going backwards with a hash line. But these can be in any position you want really. I've just got a drawing of it like this, but then you do the mirror image with the CH3 reversed, the C here, the OH there, like that, I suppose the O and the H should really be on the left, I suppose, but you get the marks for that anyway. An H on the right hand side and a CN here. So it's a direct mirror image, and you have to draw the three-dimensional representation because it asks for a three-dimensional representation. As I say, normally you can get away with a two-dimensional representation. Describe how these separate samples of each of the enantiomers could be distinguished. They rotate plane polarized light in different directions, so in opposite directions or in different directions. You've got to have the word rotate, you've got to have the word plane, and you've got to have the word polarized light in different or opposite directions. So question 3.5, let's have a look at what we've got here. We've got butan-2-ol, so I've got 4 carbons with an OH on carbon number 2, so it's a secondary alcohol because the C with the OH is in the middle of a chain connected to 2 other carbons either side. Reacts with concentrated sulfuric acid. Remember, concentrated sulfuric acid removes water. The way it does this is it removes the OH off a carbon, and off an adjacent carbon it takes an H. So it takes the OH off a carbon, and on the carbon next to it, either to the left or the right, it takes an H. So in that way it can produce 2 isomeric alkenes, 2 isomers with a double bond, because what it does is when it takes the OH off, if it takes the H to the left and removes water, it leaves a double bond between those 2 carbons, or if it takes an OH and then removes an H to the right, it creates water and really produces a double bond to the right of the COH. We'll have a look at that with the mechanism in a minute. So it produces 2 isomers, 2 positional isomers where the double bond is in a different position depending on which H is taken along with the OH, either to the left or to the right. The third isomer is probably going to be an EZ isomer. We'll have a look at that when we make it. Name and outline a mechanism to show how one of the alkenes is formed. So we've got a double bond and it's a mechanism. The mechanism type is going to be elimination because you're removing water, taking water, eliminating water from something. Explain how this reaction can lead to the formation of these 3 alkenes. Okay, so removal of water is elimination for a start. Let's have a look at the mechanism. The first thing to remember is that sulfuric acid, all acids make H+, and you need H+ in the mechanism, not H2SO4. You don't want the full formula of the sulfuric acid, just H+ for sulfuric acid in the mechanism. The butan-2-ol has a lone pair of electrons on the O of the OH, which is going to attack the H+. Let's have a look at the mechanism then. So we've got a lone pair of electrons on the OH of butan-2-ol. So 4 carbons in the line, the OH is at carbon number 2, and I've got a lone pair of electrons there on the OH. It attacks the H+ from the sulfuric acid. When it does that, then the electrons are moved onto the H+, and it neutralizes, takes away the H+, the plus of the H, because the electrons, which are minus, are transferred onto the H+, or bonded to the H+, and that removes the H+. The O has had electrons move away from it, and therefore that becomes plus. So this becomes OHH, because the O has bonded to that H, and it's got another H, so it's OH2, or you could write it as OHH as a displayed formula, and the plus is on the O, because electrons have moved away from the O. Now what actually happens is, this is ready to be released as water, so the bond breaks on the COH2+, the bond breaks and goes on to the plus of the oxygen. That's going to break off H2O, and the plus disappears off the oxygen because electrons have been moved from the bond onto the plus and it neutralizes it. So that will make water. At the same time, this carbon then, if we're not careful, is only going to have 3 bonds. 1, 2, 3, because this bond's broken. So the H of an adjacent carbon breaks off and the electrons move between the 2 carbons, and then that'll be released as an H+, and that means that the sulfuric acid remakes the H+, and so it's actually a catalyst in this reaction, and the double bond will be here. So that will, in this case, make but-2-ene. But, 4 carbons, the OH2 plus disappears as water, the H disappears as H+, and so we're just going to end up with 4 carbons with a double bond in between carbons 2 and 3, so it's but-2-ene. This way, so what I mean is, instead of that H being broken off, if one of the H's to the left were broken off, then the double bond would be here. So if I had a H here and that released electrons into this between carbons number 1 and number 2, the double bond would be between carbon number 1 and 2, and it would make butanene. So if the H were to go from the left, because H can go to the left or be released from the left or to the right of where the OH is, either from this carbon number 1 or this carbon number 3, and that will create two different structural position isomers, butanene and butanene. Butanene, by the way, has, if you consider it, it's got a double bond with no free rotation, and to the left of the double bond I've got a C with an H and a C with a CH3, so I've got two different groups to the left of the double bond, and I'll have a CH3 and an H to the right of the double bond, so I'll have two different structural isomers. I'll have both with the CH3s on one side, a Z isomer of butane, and one where a CH3 would be on the top, where it would be above, and one where it would be below, on opposite sides of the carbon-to-carbon double bond, and that would be my E isomer. So butane forms as a mixture of EZ isomer along with two positional isomers, butanene and butanene. Okay, so I've got a reaction pathway here. Give the name of compound F. So let's have a look. It's got 1, 2, 3, 4 carbons. So it's bute, and it's a carboxylic acid. So it's butanoic acid, but it's got two carboxylic acids. So it's butane dioic acid. Butane dioic acid with a methyl group at carbons number 1, 2, and 3. So it's 2, 3 dimethyl, there's the two methyls, 2,3 dimethyl butane dioic acid. Deduce the structure of compound D. Suggest a reagent for the conversion and name the mechanism. Suggest the type of reaction occurring in step 3 and the structure of D. That's a tough question. Deduce the structure of compound D, so the middle one here. So something's happened here. CNs have replaced something on this chain that's occurred here. What do CNs replace? Well, CNs are nucleophiles. Cn minus are nucleophiles. They've got a lone pair of electron on the C, and they attack a delta plus on a C and release something like a Br. So if you had Brs on here, the Brs could get replaced by CNs. So D has got Brs where the CNs have been, because Cn minus is from potassium cyanide. Potassium cyanide would attack the C here, because this will be a polar bond. C to Br will be a delta plus delta minus there. The Cn minus ions with the lone pair of electrons on the C will attack the C here, and the Br will be released as the bond is broken, the electrons transferred onto the Br. So this is what D is. What else have we got to do? For each of the conversions in step 1 and 2, suggest a reagent for the conversion and name the mechanism. So I've got to turn a double bond here, the two double bonds I've got to break into a single and get Brs on there. So I can add HBr. HBr across this bond will add an H on the end here and a Br here, and an H on the end here and a Br here by electrophilic addition. So HBr by electrophilic addition is the reaction here to make 2,3-dibromobutane, which is D, and then to convert Cn into COOH, you actually add water. So that's a little known reaction, just something to remember. You don't need to know the mechanism. You can convert Cn into a carboxylic acid by adding water, and that reaction is called hydrolysis. So HBr by electrophilic addition, KCN, potassium cyanide, then would replace the Brs by nucleophilic substitution, and the CNs can turn into COOHs by adding water, a process known as hydrolysis. State a reagent or combination reagents that can be used in test tube reactions to distinguish between F and G. So here you've got a primary alcohol, and here you've got a carboxylic acid. So the easiest reagent is to test for the carboxylic acid. A carboxylic acid will react with sodium carbonate and produce effervescence or bubbles, whereas with G it won't. There'll be no visible reaction. F and G react to form a polymer, drawing the repeating unit of the polymer. Well, what actually happens is COOH, the OH here on the COOH, and the H of the OH, that H there and that OH react to form water. So that'll form water and it'll form a COO, an ester bond. So you're going to end up with a polyester between those two there as it releases water in a reaction called a condensation reaction. Now then, so what you're actually probably best doing is, the easiest way to do it is to draw it out again. So draw it out like this, and then remove that OH and remove that H to make water. And remember, at the other end, this end is going to react with another one of those. So it's going to go on and on and on. So if you remove the OH from this end, you need to remove the OH from this end, and if you remove the H from this end, you remove the H from that end, and you end up with this. And then all you do is join them together and make sure you've got some trailing bonds at the other ends that will react again, and that then is your answer. Question 4.5. In an experiment, 0.930 kilograms, interestingly they've used kilograms, of purified F were obtained from 1.11 decimeter cubed of G, density 1.04 grams per centimeter cubed. So immediately you've got a problem with units. You've got this in kilograms, you've got this in grams per centimeter cubed, you've got this in decimeter cubed. But one clue we've got is that density equals mass divided by volume. So density is mass divided by volume. The mass is in grams and the volume is in centimeter cubed. I've been given a volume, it's in decimeter cubed, but I can convert that into centimeter cubed, and if density equals mass over volume, I can work out the mass of G that I've got. That's obviously the way that it's leading me. So let's have a look at that first of all. Density is mass over volume. It's in grams per centimeter cubed. Density, grams is the mass, centimeter cubed is the volume. This decimeter cubed needs converted into centimeter cubed. Centimeter cubed is decimeter cubed is large, centimeter cubed is small. So large into small you multiply by 1,000. 1.11 decimeter cubed times 1,000 is 1110 centimeter cubed. Now density 1.04 is mass divided by volume 1110. Rearrange that so that mass is 1.04 times 1110. I've got 1154 grams of this. This is how much I'm reacting. So G is the reactant. That's what I'm starting with. I've got 1154 grams of this. Now I'd like moles because I've got an equation here. I know that G is being used to make F. So I'd like moles because 1 mole of this will make 1 mole of this. I'd like to know how many moles of this I've got. Well, to get moles from mass, I'm going to need to know the MR, because moles equals mass divided by MR. So let's have a look what I've got in this. I've got 1, 2, 3, 4 carbons, 5 carbons, that's a methyl group, 6 carbons. How many H's? 3 on there is 6. That's carbon's got 3 bonds, so there must be 1 on there, 7. 1 on there, 8. That carbon's got 2 bonds, there must be 2 on there, 10, 11, 12, 13, 14 H's. So 1, 2, 3, 4, 5, 6 carbons, 14 H's and 2 O's. So when I work that out, the MR of G is 118. Now moles equals, moles is mass divided by MR, so the mass is 1154 grams, divided by the MR 118 equals 9.78. So I should make I'm reacting 9.78 moles of G. I should therefore make the same amount of moles of F. I know that because 1 mole of this will make 1 mole of this. I've got the same number of carbons, the same shape, and exactly the same number of carbons in G as F. So 1 mole of that will make 1 mole of F. So 1 mole of G makes 1 mole of F. So 9.78 moles of G should make 9.78 moles of F. Great. MR of F. So I've got the number of moles of F. I want now to work out from the MR the mass that I've got. I'll work out the MR of F. Let's just see what it is. 1, 2, 3, 4, 5, 6 carbons. That's 6 12s. How many hydrogens? 3 on there. 3 on there is 6. 7, 8, 9, 10 H's. Each of those got an atomic mass of 1. And I've got 4 oxygens, 4 16s. 146. So I should make 9.78 moles of F. MR is 146. Moles is mass divided by MR. 9.78 is the number of moles that I should make. Mass divided by 146. Rearrange it, multiply those two together. So the mass that I should make is 9.78 times 146. I should make 1427.88 grams of F. That's how much I should make if everything goes perfectly. That's my theoretical yield. But I actually made 0.930 kilograms. My units don't match, so let's multiply this by 1,000 to get kilograms, a larger unit into a smaller unit, so kilograms down into grams, a times by 1,000, that's 930 grams. So I actually made 930 grams, that's my actual yield, divided by what I should make, 1427, divide those two together, multiply by 100% equals 65.13%. That's how much I should get. Let's have a look at how many significant figures. I've got 3 significant figures there, 3 significant figures there. I've got 3 significant figures here. I need 3 significant figures. So let's go for 65.1%. Question 4.6. One reason for a yield less than 100% in the previous question is that G needs to reacts to form a number of other compounds. The other compounds are all liquids. How am I going to separate the mixture of liquids? You can have distillation or fractional distillation. What kind of apparatus? Well, let's draw it. So what we've got is we've got a round bottom flask, we've got a fractionating column, we've got a thermometer, and then we've got a condenser coming down into a conical flask. If you're going to draw it, then be careful here. This tube should go all the way through this bung. Thermometer should sit here near the top of the fractionating column where the outlet's coming down into a condenser. This tube goes all the way through the middle of the condenser, and then round the outside is where the water flows. It goes in at the bottom and out at the top, and then you've got a conical flask with an open part here with no line going across, and open parts show that the top of the flask is open. Deduce the molecular formula of H. So it looks as if I've got CH3COCl with aluminium chloride. The aluminium chloride is going to remove the Cl and form AlCl4- and leave that a plus on the C. We'll have a look at this mechanism in a minute, and that's going to join onto the ring and substitute an H. So we're going to get electrophilic substitution here using AlCl3 as a catalyst. Anyway, deduce the molecular formula of H. What have I got? How many carbons have I got? I've got 6 in the ring, 7, 8, 9. I've got 9 carbons. How many O's? 1 O. And how many H's? 3, 4, 5, 6. And then on each of these I've got 6, 7, 8, 9, 10. So every carbon has 3 bonds. Now I've got a delocalized ring of electrons here which forms the 4th bond. C9H10O. I get 2 isomers. What are these? Well, I've got phenyl ethanone with a methyl. I've got methyl phenyl ethanone, but it doesn't ask you to name it. It just asks you for the type of structural isomerism. Remember, there's structural isomerism, there's 3 kinds. There's chain, where you change the length of the chain. No, I've not done that. there's a position where I've changed the position of something. Well, I've changed the position of this ethanone group here from carbon number 1, 2, 3 to carbon number 2. So it's definitely position. It's not functional group because I've not changed any of the functional groups. I've still got an ethanone group here, and I've got a methyl group here. So it's definitely position. Name and outline the mechanism for the reaction of ethanol chloride. Now, ethanol chloride is this here, CH3COCl, a double bond CO and a Cl. A very, very reactive, violent chemical, has violent reactions, especially with anything with water, and forms white, steamy fumes of hydrogen chloride. Name and outline the mechanism for the reaction of ethanol chloride with methyl benzene to produce H. Include an equation for the formation of the reactive intermediate that's involved in the reaction. So what actually happens here is this CH3COCl reacts with the AlCl3. The AlCl3 removes Cl- and leaves CH3CO. It's the C that's not got enough bonds. It's bonded to the CH3 and it's got a double bond to the O, so it's got 3 bonds instead of 4, so it's got a plus on it. So let's actually have a look what happens here. So my CH3COCl reacts with AlCl3, forms AlCl4-, that should be at the top rather than the bottom, AlC4- here, and it forms CH3CO. That plus should actually be on the C, because it's the C that's not got enough bonds, so it should be CH3C, a plus on the C, and then double bond O. That carbon's only got 3 bonds, that's why it's got a plus. The mechanism, so the mechanism for the reaction is that you've got this methyl benzene reacting. You can see now the plus is on the C because the C's not got enough bonds, it's only got 3 bonds rather than 4. So this ring attacks the C+. That joins on in the correct place. Let's have a look where it's going. It's going opposite the CH3. So if the CH3 is on carbon number 1 of the ring, this ethanone group is going on carbon number 4. So I've just rotated it round, but if this is carbon number 1, 2, 3, 4, it's opposite. And I need to draw the H on there as well. I need to draw a horseshoe. Should go a little bit further round actually. That's a very wide horseshoe. Should go a little bit further round with a plus in the middle of the ring, because it's the ring that's lost electrons. Electrons have come from the ring, so that becomes plus. The C plus, the plus on the C is gone because it's had electrons put onto it, so it's neutralised the plus. And there's the COCH3, COCH3 joined on. I've drawn the H, and then that goes back into the ring, and then that is going to make my product, which is this. Phenylethanone, methylphenylethanone. A mixture of 2 dipeptides, J and K, can be separated by gas chromatography and by mass spectrometry. Let's try and explain the two then. Gas chromatography explanation. So what actually happens in gas chromatography is that you have beads in a tube, and they're the stationary phase, and they attract the amino acids. And you push an inert gas, the gas that doesn't react with the amino acids, pushes it along the tube. And what actually happens then is that in gas chromatography, the dipeptides, so the 2 peptides, J and K, will appear at different times. They'll appear at different times depending on their affinity, that means how much they stick for their affinity for the mobile and stationary phases. So how much they stick to the stationary phase, that's the beads in the tube, and how much they move or are soluble with the mobile phase, that's the gas that's being pushed through them. So how much they move with the mobile phase, how much affinity they have for the mobile phase, and how much they move with it, or if it were a liquid, how much they dissolve in it, are soluble within it, and the stationary phase, that's the beads in this case. Mass spectrometry explanation. I think both of these, if you count up the number of carbons, hydrogens, nitrogens, sulfurs and oxygens, they've both got exactly the same. So they're both going to have identical MR. So they're going to have their masses, mass divided by Z, their charge ratios are going to be the same. So they're going to have the same MR in this. So they're going to have the same MZ values. Tripeptide L. So for question 6.2, a tripeptide L is partially hydrolyzed. So tripeptide means it's got 3 amino acids. Partially hydrolyzed means that it's been broken into pairs. So it's been broken into 2s. Partially hydrolyzed. Hydrolyzed is a reaction with water and usually dilute acid or dilute base. In this case it says it's concentrated hydrochloric acid. Okay, and it produces 2 dipeptides, so 2 amino acids broken together. So one of them's broken off. One of the 3 is broken off. And the amino acids alanine, lysine and serine are the 3 amino acids in the tripeptide. So the dipeptides, the 2 amino acid that are left behind after the hydrolysis, could either be any of these: alla-lys, alla-ser, lys-ser, lys-alla, ser-alla and ser-lys, and we've got to determine which ones they are. So N and M are the 2 spots on the paper chromatography experiment there that I've got, and so what I need to do is I need to now draw some grid lines on. And I count from the start line up to the middle of spot M, and it looks as if it's about 2.5 grid lines up. And then I count from the start line up to the distance travelled by the solvent, which looks as if it's about 18 squares up. So 2.5 is the height of the middle of the spot of M, divided by 18 comes out at about 0.16. So the closest one for M is ser-alla. My other one, N, looks as if it's about 9 squares up from the start line up to the middle of the spot, maybe 10, let's say 10 divided by the 18, 10 divided by 18 is 0.55, so N must be alla-lys. Ser-alla and alla-lys. Order of the amino acids in the tripeptide. Well, alla's got to be in the middle, so ser-alla and alla-lys, so it must be ser-alla-lys, and therefore when it's broken either the ser off and left the alla-lys, or it's broken the lys off and left the ser-alla when it's been hydrolyzed. Let's have a look at the extract from a data book now. So what I do here is I imagine that glucose is bad for you, and I put a big cross. And I know that the OH is here and the OH is here on the phosphate, and the 2-deoxyribose bond with each other, because the OH and an OH makes water and leaves an O left over as a link, as a bond. So this OH, this phosphate here with the top OH, links onto the bottom OH of a 2-deoxyribose, and the bottom OH of another phosphate links into the top OH of one of these here. I'll explain what this one does and what these bases are all about in a minute. So let's have a look at the question. The question says, using the information from the data book to help you answer this question, work out how a single strand of DNA is made from nucleotides linked together. So I've got a phosphate, and then I've got a 2-deoxyribose, and then I've got a phosphate. And we've talked about the fact that this OH and this OH here bond, so a phosphate above using the bottom OH linking to this OH, and a phosphate from below using its top OH linking to the bottom OH here. It doesn't really matter which O and H's are lost. You lose 2 H's and an O somehow or another from the OH and the OH, and then again here, and therefore if I remove an H and an OH, doesn't matter which H and OH here, I end up with this. So the H has gone and the OH has gone, the OH has gone and the H has gone, and then when I link them together with a drawing, by putting a bond in, an O to a CH2, and then this bond extended down to the O. I have got my phosphate 2-deoxyribose phosphate link. Now it says that the structure of a nucleotide that contains guanine links on. So let's have a look at these bases. These bases link on to the phosphate 2-deoxyribose phosphate, so the main strand of the DNA. The bases link off it, and they use the NH at the bottom. So you find the NH from your data book on the bottom of each of these, and it's the NH that links to this OH here. So this OH here on the 2-deoxyribose links to an NH on a base. And no prizes for the fact that the O and the H and one of the H's, OHH or H2O, are made, and therefore you rub out an OH and an H and it leaves an N to a carbon link. Let's have a look at that now. I'm going to use guanine because there's guanine in the question, and I'm just going to turn it round. I'm just going to rotate this. Forget about what the other circles are for. We'll do that in another part of the question. This NH here, or this NH here of thymine, cytosine, thymine, and adenine, could be the same thing. This NH, let's have a look. This NH, I've just rotated guanine so I can get in the right orientation. This NH links with an OH, removes the water, so I've drawn it again without the water here. I've removed the water, so I've removed an H and an OH here, and now I'm ready just to put the link on. I've left the rest of it the same. So I've removed the H and the OH, and now I'm just ready to put the link on. And you could do the same, so if you're asked for adenine or cytosine or thymine, you could do exactly the same. It just rotates round slightly, or you can flip it, so flip it over left to right, turn it left to right, transpose it left to right to get it in the right orientation here. Now, on the other part of the data book, you may have noticed some of these rings here, the red rings. The red rings highlight single N's and single O's. Single N's and single O's, this N as well, you could put them on as well, these N's as well. Any single N's and any single O's have got lone pairs of electrons on. So you draw lone pairs of electrons on the N's and the O's. And then you do what I call the Ghostbuster effect. You don't let the streams cross. And so you end up with 5 intermolecular hydrogen bonds. Okay, so you've got bonds here, an N to an H is a delta plus, because you've got a hydrogen bond in the NH and you've got a lone pair of electrons on the O, so we can link those to the top two easily. Then we go round one either side, and the lone pairs of electrons on the N link to the delta plus on the NH, because the H is the N is very electronegative, so that's going to be a polar bond, forming a hydrogen bond with that lone pair there. And then we go round again, the lone pair on the oxygen can form a hydrogen bond then with the delta plus on the NH, because that's a very polar bond, a hydrogen bond here, very, very polar bond, forming a hydrogen bond across to the lone pairs of electrons on the O, because the N here is electronegative. Electronegative large delta plus bonding across to the O. So I've got 3 bonds between guanine and cytosine, and the streams, the bonds, the hydrogen bonds, don't cross. In the remaining part of my Ghostbusters picture, I've got the 2 bonds here, one from the top on the lone pairs of electrons on the O, linking to the delta plus on the NH here, this very, very polar bond with the N being electronegative. And here I've got another polar bond with the N being electronegative and a delta plus, finally going around the outside to the lone pairs of electrons here on the N. So I have 2 sets of intermolecular bonds, hydrogen bonds between the adenine and thymine, and 3 between the guanine and the cytosine. Let's have a look at my question now. It says, how does this complementary strand in a helix, how complete the base pair diagrams showing the interactions? So let's try and identify this first of all. I've got an NH2, an NH and an O, an NH2, an NH and an O. There it is, NH2, NH and an O. This is guanine. Guanine here, I can identify as guanine here from my O, NH, NH2N, O, NH, NH2N. I can identify it here in my guanine O, NH2, NH2N. It's slightly turned round in this picture here, but that's guanine. So what will guanine link with? It will link with cytosine. So what I do is I draw a cytosine alongside. And now what I do is I work out what's going to bond to what between guanine and cytosine. Well, on the guanine, the O with the lone pairs of electrons is going to link to an NH2 on a cytosine. The O with the lone pairs of electrons here is going to link to an NH2 with the cytosine. What else? I've got an NH on the guanine linking to an N lone pair, an NH on the guanine linking to an N lone pair, and then finally I've got an NH2 on the guanine linking to an O lone pair, an NH2 on the guanine linking to an O lone pair. The problem is my streams cross, so I'm going to have to flip this over like this, flip it over, I'll show you it back again, flip it so that the NH2, the N and the O line up properly, flip it, and then the streams don't cross, or rather the hydrogen bonds don't cross. Now even better if you drew the lone pairs of electrons on the O and the lone pairs of electrons on the N and the lone pairs of electrons on the O and the delta pluses on the H's of the NH, NH and NH here, and that will get you all of the mark. State how the interactions between adenine and thymine differ from guanine cytosine that we've just done in 7.2. So we did guanine cytosine here. Guanine to cytosine that forms 3 hydrogen bonds. How do adenine and thymine differ? Well, they only form 2 hydrogen bonds. There are only 2 hydrogen bonds between adenine and thymine. Urea has the displayed formula, looks like this. It's got an amide group in there, or a peptide group, a C double bond O to NH. And this will have an N joined to an H is going to be very polar. That's going to have a delta plus and a delta minus, because an N to an H forms hydrogen bonds with another N to an H. So anytime you have an H joined to an O, an N or an F, then you get different electronegativities and you get a very large delta plus, a very large polar bond forming a hydrogen bond. So this is going to form hydrogen bonds. So that's all it does. It replaces the bases and forms hydrogen bonds with the DNA instead of these bases. So the NH2 groups in urea are going to be very polar and they'll form hydrogen bonds with the DNA instead of the bases. Hydrogen NMR and carbon-13 NMR and infrared spectroscopy are used to distinguish between compounds and identify them. Give the skeletal form of the compound that's used as standard when recording 13-carbon NMR. It's something called tetramethylsilane. It's a silicon atom surrounded by 4 methyl groups. The skeletal formula will therefore look like this, because the methyl groups are ends of lines or corners of lines without the hydrogen showing. 4 isomers, P, Q, R and S. The carbon-13 spectra are shown on the next page. The first one has 4 peaks, the second one has 4 peaks, and the bottom one has 5 peaks. So let's have a look how many peaks they produce, how many different carbons there are. Well, this is off center, so it's not symmetrical, so that's carbon in one environment, a CH3 joined to a CO, 1, 2, and then that CH2 is joined to a CO, 3, CH2 joined in the middle, 4, CH2 joined to a CH3, 5, 6. That's got 6 different ones. So P doesn't feature at all. None of those are P. There are no 6 peaks. So we're looking between Q, R and S. Q has these two CH3s here are the same, so that's 1, 2, 3, 4, 5. Q has 5 different peaks. And R, those 3 methyl groups are all the same, so that's 1 carbon environment producing 1 peak, 2, 3, 4, and this one, 1 for each of the methyl groups, 1, 2, 3, 4 as well. So R and S have 4 and Q have 5. So the 5 is Q. There's nothing with 6 peaks, so P doesn't feature. Now we've got to decide between R and S. So between R and S, the only thing I notice is that Q here has a peak with 2 peaks very close together, which is very similar to this one. This one looks fairly similar to Q. That one's offset and it's got an extra peak. But this peak here, this double peak here, very close, seems very close to Q. I'm going to look for something between R and S that's similar to Q. Something between R and S that's similar to Q. I think the one that's most similar to Q is R. So I'm going to go with R as this one and this one as S. Identify from the infrared spectra, we've got C6H12O2 and I've got to find out what's in each. Well, they've all got a CH, so CH is at 3000, so this peak here is 3000, that's the CH, and the CH here is hidden by a broader peak here. This one's an OH, so it's got an OH, a broad peak at around about 3500, and this one has got an OH as well, a rather broad peak at around about 3000. So this one has got an OH here, it's got a CH here, and it's got a C double bond O here, about 1500, 1600, maybe 1700. It's got a CO, so it's got an OH here at 3500, a CO here, but it hasn't got a signal at 2500 to 3000. It's got nothing in this region, so it's not a carboxylic acid. It's got an OH and a CO. Remember, we're looking to try and identify the 2 O's. So in T, there's an OH and a CO. That then covers both O's. That means both O's are taken care of. The U has a peak OH here. That's a broad peak. Then it's got CH here at 3000. It's got nothing else apart from the fingerprint region. So it's only got an OH, but it's got 2 O's, so it must have 2 OH groups. And V, finally, what's V? V 3000, big broad peak, is an OH. It's got an OH in there, and it's got a CO in there. And this broad peak here is also showing a carboxylic acid group, probably. The carboxylic acid group has a signal at 2500 to 3000, somewhere around here, and it has got one, not like this one that's missing it. It's got a very broad peak here. I think that's a carboxylic acid. So 8.4, so I've got hydrogen NMR. So I've got C6H12O2, and I've got some chemical shift patterns, some integration values, and some splitting patterns. I need to lay this out as a table here. I need to keep the same format for this table. As soon as I start writing it as free text, I lose track of what's what. So first of all, deduce the simplest ratio of the relative number of protons in each environment to compound X. That means get these numbers into whole numbers. So the integration value is the heights of the peaks, and that will tell you the number of hydrogens in each of these 5 different groups. So I've got 5 different pieces, 5 different jigsaw pieces that I've got to determine what they are in this compound. So I've got 5 different jigsaw pieces, and each of the jigsaw piece has a different set of hydrogen environments. So in this jigsaw piece, in this chunk, the hydrogens are in the same environment. They're connected, bonded to the same atoms. So are these, so are these, so are these, and so are these. So they're all I've got 5 different hydrogen environments. If I was to draw it out with circles and squares and triangles, etc., I'd have 5 different shapes for my hydrogens. So I've got 5 different peaks. So let's have a look now. How can I sort out this integration value? I've got 0.6, 0.6, 0.6, 0.9 and 0.9. So what I do is I divide by the smallest. I divide by 0.6, and then that gives me 0.6 divided by 0.6 is 1, 0.6 divided by 0.6 is 1, 0.6 divided by 0.6 is 1, 0.9 divided by 0.6 is 1.5, 0.9 divided by 1.5. I multiply up, so now I've got 2, 2, 2, 3 and 3. And that gets me my 1 mark for this question. But I'm just going to take it a bit further. Once I've got it in this table and I've got it laid out like this, I'm just going to put some extra information in underneath. If I've got 2 hydrogen environments the same, it must be a CH2. 2 hydrogens bonded to the same carbon. 2 must be a CH2. 2 must be a CH2. 3 must be a CH3. And 3 must be a CH3. And these 2 CH3s are not bonded to the same carbon. Otherwise, those 6 hydrogens, the 2 methyl groups, if they're both bonded to the same carbon, those 6 would form at the same peak. They'd be on the same peak, and I'd only have 4 different carbon environments rather than 5, and I'd have an integration of equivalent to 6 instead of 3. That peak, instead of 0.9, would be double that. It would be 1.8. So I have got 2 different sets of CH3s bonded to different parts of the molecule. Now what do I know? While I'm here laying out a table, I might as well say that this CH2 is bonded, it's given a triplet, so it must be bonded to a CH2. 2 hydrogens give a triplet, so it's bonded next to a CH2, which are going to split these hydrogens into a triplet. A quartet means that this is bonded to a CH3. 3 makes a quartet, so its neighbouring carbon has got 3 hydrogens. A triplet, so this CH2 is bonded to a CH2. Those 2 hydrogens create a triplet, split this CH2 here into a triplet. This one's a singlet. Now this one's interesting. A singlet means that this CH3 is bonded to a carbon with no hydrogens, or maybe an O. A carbon or an O, something with no hydrogens at all, is bonded to this CH3. So that's quite interesting. And then this CH3 is bonded to a triplet, is bonded to a CH2. A CH2 will split this into a triplet. So now I've got some more information than I had before. Let's have a look. Use the data in the table in the data booklet to help you answer this question. Deduce the part of the structure that causes a shift of 3.5 and the part of the structure that causes a shift at 2.2. Well, before I go on to that, I'm just going to try and investigate what this might be first of all. Could it be that this purple CH3 is next to a CH2? So it could be one of these CH2s here, and I've labelled them up in colours. This CH3 here, here at the end, let's say, is next to a CH2. Which CH2 is it next to? It's got to be to the red one, because the red one's next to a CH3. These two are next to CH2, so I put the red one in next. This red one is next to a CH3, that's right. What comes next? A blue one. A blue one is next to a CH2, a yellow one's next to a CH2, so I'm actually not sure which way round these will be. So I've got a blue one to a CH2, that's correct, and this side a CH2, a yellow one, that's correct, and my yellow one's to a CH2 as well this way. So these two, this blue and this yellow, could be either way round. They're bonded to CH2s. My CH3 is bonded to a C or an O. So my CH3 then at the end, there's something in the middle here, which is either a C or an O. And just by a process of subtraction, there are 6 C's in this, and I've got 1, 2, 3, 4, 5. I'm missing a C, and I'm missing 2 O's. So somewhere I've got to fit in a C and 2 O's. And that one here, this question mark, doesn't have any H's in there. I think I've accounted for all the H's. 12 H's, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yes, this has no H's in it, and I know that because this CH3 is next to a C or an O with no H's because it's given a singlet. Okay, let's have a look at what's next. So, this 3.5. 3.5 I've identified as R, which is anything, O, C, H, and that H there that's bold is the one that's giving this shift pattern of 3.5. So that H there is given a shift pattern of 3.5. Let's have a look which one gives a shift pattern of 3.5. That's this column here, 3.5, which is my red CH2. My red CH2 gives a split of 3.5. So those hydrogens on that red CH2, a hydrogen here, one of those hydrogens is bonded like that with a CO. So my red CH2, it might have another H up here, this CH2 is bonded to an O. So my red CH2, which gives a splitting pattern, a shift value of 3.5 to 3.9, 3.5 here, 3.5 fits in between 3.1 and 3.9, has got, my red CH2 has got an O bonded to the C of the CH2. There's an O bonded to the red one. Could it be CH3, CH2? Could there be an O there? CH2O, because I know the CH2 is bonded to an O. That gives me an O, one of my O's that's missing. Okay, 2.2. 2.2 is this one here, a chemical shift, a shift of 2.2. That's my green one, my CH3. My CH3 gives a shift of 2.2. 2.2, if I look up 2.1 to 2.6, 2.2 fits in this, is this. So R can be anything. My CH, that H of that one there, which is my green CH3, my green CH3, CH3, so there must be 2 H's here, but that H on the CH3, this is my CH3, is bonded to a CO. So my CH3 is bonded to a CO. I found that question mark there. That CH3 is bonded to a CO. I know it's now this chemical with a CO in the middle, and then that matches my C6H12O2. 9.1. This is the Arrhenius equation. Natural log of your rate constant equals activation energy, negative activation energy divided by the gas constant divided by the temperature in Kelvin, plus natural log of a constant called the Arrhenius constant. So first of all, it guides you through. You've got the rate constants here. You need to press the natural log button and work out natural log of each of these rate constants, and you need to divide each of these numbers into 1. So 1 divided by each of these numbers, and you should end up with a table that looks like that. When it now says plot a graph of natural log k against 1 over t, you always do y against x. So natural log of k, ln k, goes up the y-axis, and 1 over t goes along the bottom axis. Now when you're plotting the bottom axis, you can just use these whole numbers, 1.43, 1.38, 1.34 and 1.26, and put times 10 to the minus 3 in brackets on your label. And then you should end up with a graph that looks a bit like this. It will come down, it'll be a straight line as long as you label your axis. Put natural log of k up the y-axis and 1 over t along the bottom axis. You put your points, plot your points accurately, and your line, draw a line of best fit through the points, and it covers at least half the graph paper. You'll get your marks for drawing your graph. Now the gradient is the change in y divided by change in x. So you measure the change in y and you divide by the change in x, and it will come out as a negative number, minus 2.88 times 10 to the minus 4, or close to that. Because the line is coming down in this way, it's a negative number. Now you may remember from GCSE maths, y equals mx plus c, so m is your gradient and c is a constant, and that resembles this equation here. Y, your y-axis, equals your x-axis is 1 over t, and this is a constant. So the rest of it, minus EA over R, is your m, which is your gradient. In other words, minus EA over R is your gradient. So if you reverse both signs, then 2.88 times 10 to the power of 4 equals your activation energy divided by your gas constant, 8.314. Multiply the two numbers together, you get EA, and that is in joules per mole. You know it's in joules per mole because your gas constant is in joules per Kelvin per mole. So it actually wants it in kilojoules per mole, so to convert small joules into kilojoules, then you're dividing by 1,000, so 2.39 times 10 to the power 3 joules per mole equals 239 kilojoules per mole.